Hi, Suva Music Technology. Today we're going to continue our analysis of this LPB-1 circuit. It's effectively a common emitter amplifier. This time we're going to do a small signal analysis. We're going to convert the circuit to its AC equivalent, analyze the transistor using a model, calculate and then measure input impedance, do the same thing for output impedance, and then we're going to calculate and measure the frequency response. So let's get going. First of all, let's remind ourselves of the different components in this circuit. So this is our AC coupling capacitor, C1 on the input, and then C2 on the output. We have R1 and R2, which form our voltage divider bias on the base of the transistor. Here on the collector we have RC, and on the emitter RE. And then we have this attenuation here in way of RV1, let's call it. So the first thing we need to do to this circuit to convert it into its AC equivalent is to short any DC power sources, because if you remember from a previous video, the AC doesn't see this DC 9 volts. So we can simply draw in a ground there and there. And the second thing we're going to do is we're going to assume that any signals that we're interested in are just going to pass straight through C1 and C2, so we can effectively just short them out like this. So now we've done that, we can bring RC down here, and we can bring R1 down here, and we can redraw this to simplify it. And we end up with this simplified version of our circuit. Now let's just remind ourselves what each of these are. This is R1, this is R2, this is obviously on the emitter, so it's RE. This is coming from the collector, so that's going to be RC, and this is our output attenuation, RV1. Now hopefully you'll see that these are in parallel. So we can simplify that by saying this is R1 in parallel with R2, and it can just become one resistor. This is RE, of course, RC, just as above, and RV1. Now I think we can work out R1 and R2 because we'll use it in the future calculations. So let me just bring in the calculator and move the pedal. So we need our parallel resistors equation, and there's only two of them, so it's the product over the sum. So first of all, we need to remind ourselves that R1 was equal to 430k and R2 was equal to 43k. Now we can simply do the product, 430k multiplied by 43k over the sum, 430k plus 43k, and that gives us, turn this on, so it's 430 times 10 to the 3, because it's kilo ohms, times 43 times 10 to the 3 equals, and then we're going to divide that by, well, I can do some of this in my head, 473 times 10 to the 3 equals 39.09 kilo ohms. So this resistor here is 39.09 kilo ohms. So now we need a way of modelling Q1 here in order to work out things like the input impedance of this circuit. So let's do that. Here we have one possible model of a transistor. This is called the hybrid pi model. You'll also come across other models such as the T model, but we're just going to stick to this one for now. The reason it's hybrid is I'm only using one resistance here, the current source, and I'm ignoring the output resistance because it's going to be so high that it won't actually affect our calculations. But maybe we'll return to this in future and look at it using some other models. For now, we're going to stick to this one. So it might look a bit strange, but if I start writing in some of these values of these components, it may become a little bit clearer. So this is RC, this is RE, these are the resistors that we saw in our DC circuit, and this here is R1 in parallel with R2. This is called R pi, and this is our current going through our transistor, which is beta IB. So from that, you may be able to work out that this is the emitter, this is the collector, and this is the base. And this represents a resistance and a current source. Okay, so let's write down what we know of these values. So we know R1 in parallel with R2 was 39.09K because we calculated it just now. We know RC is 10K. We know RE is 390 ohms. We know beta is 400. And we know that IC, which is effectively beta times IB, is 0.5 milliamps. What we need to work out is what R pi is, and it equals beta divided by GM. Now we haven't seen GM before, we don't know what it is. So GM is something known as transconductance. Now if you look at our model, we've got a current here running through R pi, and we're controlling a bigger current source here. So we're current controlled current source, which makes sense for a bipolar junction transistor, but wouldn't make sense if we were using a FET, which theoretically draws no current. Then we begin to think of those things as a current controlled voltage source. Now it still makes a little bit of sense here because we've built a voltage amplifier basically, but I'm going to stick to using the current terms, B beta times the base current, or IC in our case, to describe what's going on here, just because we're familiar with these terms and we've used them in this series up to this point. But we'll return and look at this in more detail in the future. Okay, so transconductance is measured in Siemens, not the company, the scientist, and it's a capital S because a lowercase s would of course be seconds. How do we calculate it? Well, GM equals IC, which we already know, divided by something called VT. And we haven't come across this yet either. This is thermal voltage. And you'll be pleased to know that it's the same at room temperature as 25 millivolts. Some people use 26, so you'll probably see 25 or 26 used in calculations. I'm going to use 25 because I've got 0.5 and 400, so it just makes the maths a little bit more elegant. So we can actually calculate this now because we know we've got an IC of 0.5 milliamps and we're dividing it into 25 millivolts. So 0.5 over 25 is the same as 1/50th, which is 0.02 Siemens, or 20 millisiemens. So now we can calculate R pi, because R pi equals beta 400 divided by GM, 0.02. And if you do that, you will get 20,000, I suspect. 400 divided by 0.02 equals 20K. So the value of R pi here is 20K. Now this is not a resistor, it's a resistance. So just bear that in mind because it's a model of a transistor. And it's a small signal model as well, I need to point out. These models change when you get larger signals. Okay, so we know R pi is 20 kilo ohms. So without RE, if we didn't have RE, so let's do this in red, So without an emitter degeneration resistor, our input impedance would be R1 in parallel with R2 in parallel with R pi, which equals 39.09 in parallel with 20k. And we can see 20k is less than 39, so it's going to be closer to 20k than it is to 39.09k if we didn't have RE. So we can run that calculation. So let's do the 1 over Z in equals 1 over 39.09k, let's put the point in there, plus 1 over 20k, which means that Z in equals, so let's do that, and let's do it this way, 39.09 times 10 to the 3, and then to the minus 1, which is the same as doing 1 over, plus 20 times 10 to the 3 to the minus 1 equals, and then I need to take the reciprocal of that, and I get 13.23k. So that our pi value is significantly pulling that down. Now the way around that is to introduce emitter degeneration resistor here, and it will increase our pi. Well, it won't increase our pi, but it will increase the resistance of that in combination with R pi greatly. So let me just change color again. So with the emitter resistor, we will now have Z in equals R1 in parallel with R2 in parallel with R pi plus beta plus 1 times RE. And you can already see that's going to be a big value because it's 401 times 390. And then we add R pi to it. So let's do that. 401 times 390 equals 156.39k plus another 20k from our R pi. 176. $390. Okay, so now we've got to put that in parallel. So we can do that equation again. 39.09k plus 1 over, but now it's 176,390 or 176.39k, depending on how you want to look at it. Sorry that my units are not the same here. Maybe I should just correct that a second. Get this up, 176.39k. And obviously that's going to equal 1 over, so we need to take the reciprocal. So with RE, Z in is going to equal 39.09 times 10 to the power of 3 plus 176.39 times 10 to the power of 3. And I've missed my reciprocal, haven't I? So that's got to be to the minus 1. And so is that. And then I need to take the reciprocal of this answer. And I get 32k approximately. So 31,998 is 32 kilo ohms for all intents and purposes. So look at how the input impedance here started off at 13.23 and it was being pulled down by R pi, and now it's 32k, which is a lot closer to our 39.09k of these resistors in parallel. So it's no longer pulling that value down as much as it did before. It's more than doubled it just by adding that small degeneration resistor there. Now another thing we can do is we can now do a much better gain equation. So let's have a look at that next. Okay, just using a different color here. So before we saw that the gain, the voltage gain, was equal to RC divided by RE, which was 10K divided by 0.39K, which is the same as 390. I'm just trying to keep my units the same, which equals 10K divided by 390 ohms, 25.6 approximately. But actually, it's AV equals RC divided by RE plus 1 over GM. So it's the reciprocal of the transconductance here. So 0.02, 1 over 0.02 equals 50 plus 390 equals 440. So if we take that 10,000 now, that 10K there, and we divide it by 440, we actually get 22.72. 22.7. And this is a much better gain equation because it takes into consideration the transistor and this R-pi resistance here that we've modelled by using the transconductance. So let's just jump onto the breadboard and have a look at if our gain is closer to this or closer to this. Now you probably remember from the last video it is actually closer to this, but let's just check it out again and see how much closer we now are. So here we are with our function generator feeding in 1 kilohertz at 200 millivolts peak to peak, which is reflected on the screen down there. It goes up and down occasionally, and we're getting about 4 volts peak to peak out. So that's a voltage gain of 20 actually, but it's closer to the 22 that we just calculated rather than the 25 that we had during our DC analysis. So we're much closer to this gain than we are to this gain. So this is giving us a much more accurate estimation of what the gain is of our circuit. Now also we worked out the input impedance was 32 kilo ohms. Well, we can actually measure that using a function generator and either an oscilloscope or a RMS voltmeter. So I'm going to use my oscilloscope and function generator, and we can jump over onto the breadboard and actually set up an experiment that measures this. But first of all, let's look at how to set up that experiment. So this is a pretty simple one, but it takes a tiny bit of thinking to get it right. So we have a function generator generating a known frequency at a known RMS of voltage. So let's say we're going to send 1 kilohertz at 100. Actually, that's probably a bit low. Let's send it at 200 millivolts RMS. First of all, we'll send it straight into our oscilloscope and we'll make sure that it's 200 millivolts and we're seeing that on the RMS. Then we'll remove this and we'll send it through a potentiometer first and then into our input, and we'll also hook up the oscilloscope to the exact same input. We are not using the output. I think I might make that very clear. We're not using the output. So we're not going through the pedal. We're simply wiring a function generator to a potentiometer into the input, and then we're measuring the input. What that does is effectively make a voltage divider between this potentiometer wired as a variable resistor. I'm going to use 500K, but you can use a meg ohm, and our pedal. So it looks like this. So here's our 500K, and then we've got our unknown impedance, input impedance in this case. So this is DUT, means device under test, which is the pedal. Then what we do is we set our part until we get half of the RMS voltage. So if I'm feeding 200 in there, I'll be looking for, in this case, 100 millivolts RMS. And then what I could do is simply take that resistor out of the circuit and use my measuring device to measure the resistance, or indeed a multimeter, anything that can measure resistance, measure the resistance across this resistor, and it'll be the exact same as the input impedance in our pedal. So let's give that a go. So I've set up for measuring the input impedance with my potentiometer wired as a variable resistor here, and I'm measuring the input of my circuit, and this indeed is the input of the function generator going to the exact same place as the scope probe. Notice that I'm not using the output at all, and all my grounds are wired together. So what I've got going on here is I'm setting up, by bypassing the potentiometer to begin with, 200 millivolts RMS at 1K in this case, as long as the frequency remains the same and is a frequency that's going to be used by the pedal, we're okay. I'm just using 200 millivolts because that's what I'm set up to, seems like reasonable for this pedal, but all we really care about is when it gets to half that. So now what I'm going to do is I'm going to wire in my potentiometer by moving this jumper, and we're going to reduce it until this gets down to 100 millivolts. So that's going to be around there. So now I'm going to get my component tester, and I'm going to very carefully take out the potentiometer, try not to move the setting, and I'm going to move it over to here. And of course you could just measure it in circuit, that's probably easier. And we've got about 31.5 kilo ohms, which is really close to the 32 that we calculated earlier. Okay, so we can see our input impedance equations worked out quite well, and we tested them on the oscilloscope. So now let's do the same thing for the output. And it's slightly more complex here. So people will tell you that RC, which we know is 10K in our case, is the output impedance of a common emitter. It's equivalent to RC, and they're correct. But of course, in our circuit, we've got this attenuator here as well, which is also a resistor, a potentiometer. We're using it as a voltage divider basically on the output. And we know that's 100K. And the fact that it's in the actual circuit a logarithmic part, although I don't think that one is, it doesn't matter to our equation. But you should be able to see here at full volume it's 10K in parallel with 100K. So 10K in parallel with 100K. So we know that's going to be towards this value, and that is going to be the highest output impedance. So let's bring in the calculator and do some maths. I'll just move the pedal out of the way again. Okay, so actually let's do it this way, my favourite way, to the -1 plus 100 times 10 to the 3 to the -1 equals, and then take the reciprocal of that, and we get about 9K. Here, I've put in a little bit of resistance here because obviously it's going to go down to 0, but it's not actually going to get to 0 in reality. So let's say this is kind of 99% of the way there instead, and that's going to put 1K there. This is 10K, of course, and then the other 99K is here. So let's just calculate for that. So now we've got 10K plus 99K in parallel with 1K. Now hopefully you're just going to say, yes, Stu, that's approximately equal to 1K, because this is so big that it's not going to affect that 1K. Okay, let's just check that. Just don't take my word for it. So 109 times 10 to the 3 to the minus 1. 109 I got from adding 10k to 99k, by the way. Plus 1 times 10 to the 3 to the minus 1 equals, and then we'll take the reciprocal of that, and we get 990.9 ohms, so pretty much exactly 1k. Now, hopefully you're thinking, yeah, but I'm going to use this in a pedal chain, and sometimes I'm going to plug it into a pedal or an amp. In fact, all the time when you use it, you're going to plug it into something, and that's going to present a load there, which is also going to be in parallel with this. So the load, remember that the load's also going to change this. Now 9k's not bad, 1k's a lot better, but the load will have an effect on it as well. So it will actually matter where you put this in your pedal chain. So now let's go and do the exact same thing that we did for input impedance, and have a look at how we measure that, and then jump onto the oscilloscope and actually measure and see if we get similar values to this. So again, this worked quite well for measuring the Z in. So now we're going to use it to measure the Z out. And of course the output of a pedal is on this side, as you can see here. So we're going to be taking that around to there. And then obviously that goes to the oscilloscope. So now we're measuring the output of the pedal, and note, input not used. So it's exactly the same circuit, we're just coming around the other side. I'll probably do it on here again, like I did with the input on here. Same concept, same idea, should give us a different result because the input and output impedances are different. So let's jump onto the lab equipment and have a look. Okay, very similar setup to measuring the input impedance, but note now I'm not using the input. I've got some of my grounds wired up to the output, but the oscilloscope probe is here on this red wire, and the function generator is on this yellow wire, and I've just set it up for hopefully 200 millivolts peak to peak. We just increase the amplitude till we get there. 200 millivolts peak to peak. There we go. And now what we're going to do is swap this wire, and we're looking for 100 millivolts again. It's gone way too far already. So it's around about there. So let's take this out now and measure the output impedance with the potentiometer on full. So the volumes, it's not attenuating any of our signal basically. So 9,120 ohms. That's what we calculated, 9k. Now let's move the output potentiometer slightly and try the same thing. Okay, so if I take this all the way down, I'm not going to get any signal. So I'm just going to back it up to where we're getting 200 millivolts. Roughly. Somewhere around there. And then I'm going to do the exact same thing with my variable resistor. Set that down to 100 millivolts. There we go. Take this out. So now I'm getting about 5.8k on that particular setting. So it's less than our 9k that we saw before. But again, remember that any load you then plug this into, be it another pedal or an amplifier, will also make a difference to this figure as well. So we've seen that our measurements in the lab are similar to our calculations, bearing in mind that calculations are precise, or as precise as we can get them, and we are measuring a circuit like a bit on a breadboard, so you're getting parasitics. You also have to take into consideration component tolerances, stray capacitance and all that kind of thing. But hopefully you've seen, like I have, that is pretty close. It's close enough, it's good enough to design circuits with. So our final bit of AC analysis is the filter. Now, what I've done here basically is I've put it into Folstad to see what it came out with. So I've got C1 here, which is 100 nanofarads. Here is R1 in parallel with R2. And this was the impedance looking into the base of the transistor, which was 176.4-ish kilo ohms. Now we know that these two together actually equal Z in, which is approximately equal to 32K. So we can use that to work out this corner frequency here. So our corner frequency equals 1 over 2 pi times Z in, 32K, times 100 nanofarads. So let's do that on the calculator. So that's 1 divided by, I'm going to use brackets, 2, my pi is hidden there, so I have to press shift and then pi times, it's 32 kilo ohms times 100 nanofarads. So I just automatically think these days times 10 to the minus 9 because I've got used to this engineering notation that I was talking about in the last video. 49.73, Folstad said 49.79, so very close. 49.74, I'm going to call that, hertz. Now, you might notice that it's taken at minus 3.01 decibels and it's down here, not up here. And there's a reason for that. It's because it's taken at half the power. Half power. And I'll show you why it's minus 3. So the power equation is 10 times, because it's power, log base 10, and it's half, because it's half the power. And if we do that, you might have to put this into your calculator that way round. But I've got a calculator that I can put it in this way round. So it's 10 times log in base 10 of half, 0.5 is the same thing as half, minus 3.01. So that's why these are taken at minus 3.01 decibels, because half the power. So that gives us a corner frequency of 49.74 hertz. So now let's jump back on the oscilloscope and have a look at that in reality. So we're just monitoring the output now, and I've set an RMS, as you can see down there, of 1 volt. So what we're looking for, because we're working in volts and not power, is when this drops to about 70%, which is half the power. I'll explain why that is in a future video. So we're looking for 700 millivolts basically. So if I jump down a scale on this function generator, and then I take it down a little bit more, we're getting towards that now. And it's around here. So it's just a little bit above 50 hertz. And that will be because of component tolerances. That might not be exactly 100 nanofarads. And our resistances. And obviously we've got a slightly different beta of our transistor as well, which is going to affect other things in the circuit. But again, it's close enough. Now, you can see, hopefully, as I increase the frequency, that the peak-to-peak amplitude and the RMS of the waveform gets high. You should see it's growing, basically, on the screen. So that shows nicely that it's a high-pass filter. So there we are. That completes our small signal analysis of our LPB-1 circuit. We've worked out the input impedance is approximately 32 kilo ohms. We've worked out the output impedance is between 0 to 9 kilo ohms in parallel with any load we put on there. The corner frequency is approximately 50 Hertz, and we know that changing C1 will change that drastically. We've looked at a transistor model called hybrid pi. We've looked at the value of R pi. We've discussed the term thermal voltage, and we know it's about 25 millivolts at room temperature. And we've looked at transconductance measured in Siemens and how we can use that to effectively model some of the resistances within our transistor. So I hope that's enlightened you on the LPB-1 Common Emitter Amplifier circuit from an AC perspective. Next time, we're going to return and we're going to look at this from a modern production viewpoint and look at the components they've added to the circuit. There's a capacitor, a diode, and some ferrite bead and capacitor inductive filters in there. So we're going to have a look at what they do. And we'll also have a look at some circuits that have been developed off the back of this that are very similar, like the Screaming Bird and the Mole, for example. Until then, I've been Stu from Music Technology, and I'll see you again soon.